Particles of weight 5 Newton, 1 Newton, x newtons and 6 newtons are placed at the points 2q, minus 7q, 3,3 and 9,1 respectively. The coordinates of the centre of gravity of the system are 4, 3. Find the value of x. So, in blue we have the 4 particles, in red we have the centre of gravity. Now, the 4 particles are assumed to lie on a horizontal plane, so we are looking down on the horizontal plane in this case, and the weight vector points into the screen. So we explained all of this in a previous video. So this is our plan view. Our XY plane is horizontal. So let's get the sum of the moments of the 4 forces about the x-axis. Let's start with this 6 Newton force located at 9,1. So what we need to do is get the perpendicular distance of the line of action to the force, which is perpendicular into the screen, to the x-axis. So this is the perpendicular distance. I showed this in an oblique view in the previous video if you want to see exactly what's going on. Okay, so this is the perpendicular distance to the x-axis, but that's just the y value of this point, which is 1. The magnitude of the force is 6 newtons into the screen. So to get the magnitude of the moment of this force about the x-axis, we multiply the magnitude of the force, which is 6, by the perpendicular distance, which is 1. So we get 6 Newton meters. And we take this moment to be positive. Okay, if the value is positive, well, we take the moment to be positive. It's very convenient. So we get 6 times 1, 6 Newton meters. Okay, let's look at the force acting at the point 3, 3. So the force is x newtons. We have to determine what x is, but the perpendicular distance, as you can see, is 3. So we're going to get 3 times x. Again, this is going to be a positive moment. The moment is positive for points above the x-axis. What about the 2q, the 5 Newton force at the point 2q? 2q could be anywhere along this line, of course. Now I'm showing it up here. I'm actually showing it at the correct position. Turns out that the answer to this problem is q equals 5. But I mean, the point 2q could be anywhere along this line, anywhere along this vertical line. Okay, so we have to get this distance here, which could be positive or negative. Turns out the correct answer is that q is positive, but the point could have been down here, in which case we would use a negative value. So we just look at the y value. If it's positive, the point is above the line. If it's negative, it's below. So we don't have to worry. Position it anywhere on this line. So we multiply q by 5, so we get 5q. So if q is positive, in other words if the point is above the x-axis, this force, the 5 Newton force, will have a positive moment about the x-axis. If q is negative, that is if the point is below the x-axis, the 5 Newton force will have a negative moment. Okay, now let's get to our final force of 1 Newton. Again, I'm showing the point up here, but we can show it anywhere along this line. So this distance is q. Well, q again could be positive or negative, so we can't really say distance. Like over here, we write this as q. Right, so we multiply q by 1 Newton. So we get 1q for the moment of the 1 Newton force about the x-axis. Of course, we can simplify this. 5q plus 1q is 6q. Now we get the moment of the resultant, or sum of the forces about the x-axis. So first of all we need the sum of the forces, or the resultant. Okay, so we have a 1 Newton force and a 5 Newton force and an x Newton force and a 6 Newton force. These forces are all parallel to each other, pointing into the screen. Okay, so we get 12 plus x. So that's the magnitude of the resultant force. And this force acts at the center of gravity of the system. So the moment of the 4 forces, the sum of the moments of the 4 forces about the x-axis, is equal to the moment of the resultant force of 12 plus x newtons, about the x-axis. That's provided we position the resultant force at this point. So we have to take the magnitude of the force, which is 12 plus x, and multiplied by this distance here, which is 3. So we get 36 plus 3x. So, okay, we set these equal to each other by the principle of moments, and we can solve. The x's cancel out on both sides. So we find that q is equal to 5. So we can go back up here now and write in 5 for q. Now in the next question we have to find out what x is. You see that the x is cancelled when we took the moments about the x-axis. So let's consider moments about the y-axis. So let's start with the 1 Newton force at the point minus 7, 5. So this distance here is given by the x value. Well, the distance is 7, but we will use the minus sign to indicate the direction of the moment, okay? The moment of the 1 Newton force about the y-axis has a direction that's opposite to the moment of the 5 Newton axis, the 5 Newton force about the y-axis, okay? So the directions are different, so this will come out to be negative. So we multiply minus 7 by the magnitude of the force, which is 1, so we get minus 7 Newton meters. For this force over here, we multiply 5 by 2, so we get plus 10. Okay, so these forces have opposite moments about the y-axis. What about this force here? The distance is 3. The magnitude of the force is x into the screen, of course. So we multiply x by the perpendicular distance of the line of action of x from the y-axis, which is 3. And finally we have our 6 Newton force acting at this point, so it's 6 by 9. It's 54. Okay, so the forces on the right hand side of the y-axis have positive moment about the y-axis. Forces on the left of the y-axis have negative moment about the y-axis. Simplifying, we get 3x plus 57 Newton meters. Now let's get the moment of the resultant force about the y-axis. So the resultant force is 12 plus x multiplied by the perpendicular distance of the line of action of the resultant force to the y-axis, and that's just the y value, which is 3. It'll be a positive moment. So that's going to give us 36 plus 3x. I'm sorry, this distance is 4. It's given by the x value, of course. So we get 48 plus 4x. So we equate these by the principle of moments. So we get x equals 9. So that's the magnitude of the force at the point 3, 3.